La spinach o la pisciò, sigretto tutto bello, si racchi spaghetto, ci le tua, ti la tua.
In this video, we're going to analyze the fluid mechanics of shotgunning a beer.
As we saw before, Ethel can certainly shotgun a beer. But is it a free jet? We're about to find out. Step 1 is to take measurements on shotgunning a beer. So that's what we're going to model right now. I'm going to idealize this hole that we just made as a circle. And calculate the flow rate coming out of here. Ready? Set, go. Done.
We begin by collecting measurements of a can of Pabst Blue Ribbon beer. The heights of the top and bottom of the can are shown here. We've also determined the diameter of the can as 2.5 inches, so the cross-sectional area of the can is 4.909 square inches. We'll convert this to SI units right away and have 3,167 square millimeters.
We've modeled the beer's knife wound, or shotgun hole, as a circle with a diameter of 0.348 inches. Again, we're interested in the area of this hole, which turns out to be 59.87 square millimeters.
We also weighed the can before and after pouring out the fluid. We used these values along with the volume listed on the can to calculate the density of this beer. We are going to use the Reynolds transport theorem and apply conservation of mass to this system. Our control volume is a fixed and non-deforming can of Pabst Blue Ribbon. For the system's mass to be conserved, the rate of change of mass in the control volume, our can of beer, must be equal to the sum of the mass flow rate into and out of the control volume.
Now we've assumed that the beer is a free jet. Using Bernoulli's equation, with the pressures at the surface of the beer and the orifice equal to each other, and the velocity at the surface equaling 0, we can derive an equation for the beer's exit velocity.
In RTT, we consider mass flow into the can to be negative because the dot product of the area vector and velocity vector in are in opposite directions. The mass flow out of the can is positive since the area and velocity vectors point in the same direction. Now we'll apply the RTT equation and solve for the time it takes the beer to empty. According to our calculations, it should take roughly 8.2 seconds. When we measured this time experimentally, we got 9 seconds. The values are close. The model we used does not account for head loss, which considers friction forces that oppose the flow of fluid, as well as pressure changes caused by the geometry of the can. By comparing the volume of the beer discharged to the time it took to discharge, we can approximate an average flow rate out of the system. We can also find the velocity of the exiting beer by applying Bernoulli's equation. We found a value of kinematic viscosity online. With these values, we can calculate a Reynolds number and describe the type of flow. Here we are using a Kool-Aid dye to simulate the beer flow within the can. As can be seen, the fluid flow is chaotic, which is characteristic of turbulent flow. This coincides with our calculation of a high Reynolds number for our beers with Bernoulli experiment.